Welcome everyone. So the last topic that I wanted to touch upon today was RL, reinforcement learning, and as I said, reinforcement learning is a topic by itself that requires at least a semester if not more of time to teach, but I will just introduce that, okay, for the sake of completeness. Now in this, I mean, now that we are talking about language models and autoregressive models, right, an autoregressive AR language model, it basically learns a distribution over a set of tokens, that is what it's doing, right. Now reinforcement learning, okay, so I'll just introduce that to you. See, what happens is, when you train these autoregressive transformers on internet scale data, so it has good, bad, ugly, everything, okay. Actually there was this nice picture, let me just show if this is the picture. So what they show is as follows, right. So when you train a large language model on internet scale data using the techniques that we just showed, what you get is this ugly looking monstrous model, okay. That's what they have mentioned as unsupervised learning here, which it is not at all usable, because it has all, see, if you train it on the entire internet, so it will have everything, right, good, bad, ugly, everything. So on top of it, what people do is what is called as supervised fine tuning, SFT. What is supervised fine tuning? You take some data, so you have, see, when you do unsupervised learning, you do not have any labels, so to speak, there is just data. Then for supervised fine tuning, you have the input and the desired response as the outputs, okay. Now use the input, let us say that you have some data on how human beings or rather what should be the output of a chat response. So some human beings have asked a question and you have generated the response and curated that, and then you use the same model and do a supervised fine tuning on top of it. Exact same procedure. The only thing is, now instead of predicting it on the next token, okay, you predict on the response. So your input token now becomes the entire question, the output token becomes the first token of the output, and then you take the prediction, append it, and then do a supervised fine tuning, because now you have the pairs of input and output, that is supervised fine tuning. So that's this pink face, that's still ugly, right. So it does not align with the human intent, okay. So if you remember, right, the head of one of these big companies told that to make your LLM say thank you, we spent a lot of dollars. Do you remember that? It just happened very recently. So that is alignment. So this the smiley that you see at the output of this entire thing is what is called as RLHF, reinforcement learning based out of human feedback. So if you have ever used these LLMs, right, they generate two responses and ask you to choose one of them, isn't that's exactly that's actually collecting data. In fact, there have been companies that have made thousands of hundreds and thousands of human beings just evaluate the response of LLM and use RL on top of it, okay.
Like the response.
So basically you are given, for a question you are given two responses, two samples, basically these are stochastic models, right. Every time you sample you get two different response, take two responses and rank order them, I mean which one is better, which one is good, okay. Then use RL, reinforcement learning framework, to align it to whatever humans prefer. See, that is why LLMs are very polite, because they have been asked to be polite using RL, okay. You can actually use RL to train a rogue LLM, right. I mean, I'm not suggesting that you do, but what I'm saying is the technique is generic.
For science research, that might be important. You want to know when you are wrong.
Exactly, right. I mean, depends. So basically the idea is that unsupervised learning is like no data at all, okay. I mean, in mathematical terms, model the marginal, supervised learning is model the conditional, RL is model the environment. That is the paradigm shift, okay. In supervised, in so far what we are doing is, we are assuming that all we have are samples drawn from a distribution, and that is it. We do not have any way to actively interact with the environment. But human learning, right, does not happen through one shot data and then doing ERM, it happens through interactions. Now RL is a framework where learning happens through interactions. So that is why the name reinforcement learning, where the setup is as follows. Let us go to the math. See, aligning LLMs to human intent is one of the multiple applications of RL. Okay. Initially RL was being used for modeling games. Okay. I mean, have you played these Atari games? I don't know, maybe you're all Gen Z, right? We have grown up playing Atari games. I mean, Atari is a company basically. It's a Japanese company that used to make games. So we used to play video games. You know, this is pre Xbox and PlayStation era. We used to, I mean, when we were kids, we used to play Atari games. They're simply board games, right, and scenario based games, which can be modeled. I mean, if you want to train a model, so in RL they are called agents. Agent to play an Atari game, then you can, people were using RL, and then people solve the problem of chess, right, and then also Go. See, AlphaGo is RL. Okay. Now, one of the striking applications of RL is to align LLMs to human feedbacks. That is why I told you RL is an entire topic by itself. It is a very interesting way of looking at things. So, this is how you model the problem of ML in RL. So, in RL we assume that there is an agent. So, I will connect these terminologies to whatever we have seen so far, right. I mean, agent is something that interacts with the environment. Okay. So, it can be somebody who is playing a game, or in this case it is the LLM and so on. So, I will connect that. So, there is an agent, there is an environment, and there is an interaction that is happening. So, what do you mean by interaction? Agent stays in one out of n possible discrete states, okay, and at every time, so there is a sense of time here, okay, because discrete time. So, every time there is an interaction that is happening. Being at one of the states, the agent performs an action.
Is dependent on the state.
Yeah, depending upon, we'll put maths around it. So, there is a state, being at a state, agent performs an action, okay. When the agent performs an action, environment gives a reward back to the agent, depending upon what action the agent is playing. When take the example of playing the game, okay, the game player is an agent. So, you press some key in your joystick, that is the action. Based on that action, the gaming environment gives you a reward. So, it is a reward can be negative reward as well. So, in RL, right, reward can be negative. So, we only use reward. So, there is negative reward is punishment. The environment gives a reward. So, this is the setting. There is an agent, it is in a state, performs an action, the environment gives back a reward, and this keeps happening. So, the agent keeps performing an action, the environment keeps giving a reward. Okay, that is the thing. And there is also something called a policy, okay, which decides what action the agent has to take being at a particular state. Okay, it is a probability distribution over the set of actions conditioned on states. It is a conditional distribution. That is called a policy. Policy is the distribution on the set of actions conditioned on states. So, that will tell you, given that I am in a particular state, I meaning the agent is in a particular state, what are the set of actions that I should perform, what distribution governs that particular action. Okay. And agent also, see, it performs an action and it moves to a different state. So, it transits from one state to the other. So, there is also a probability distribution that would decide how the agent transitions from one state to the other. So, being at state st at time t and having performed an action at at time t, the next time in the next time step it transitions to state t plus 1. So, there is a distribution, okay, that governs what state it transitions to at a given time. It is called the transition kernel. Understood, right? So, what is happening, there is an agent, it goes from one state to the other, which is governed by the transition kernel, and being at every state it performs an action. that is which is governed by the policy, okay, and depending upon what action it takes, environments gives it a reward, and this keeps happening.
This probability distribution of the next state should also depend on the reward.
No, it does not. No, the kernel's transition kernel does not depend on the reward. Only policy depends on reward. We'll get to that. Okay, and an RL, right, is quantified by this thing called Markov decision process, which whatever I just described is called a Markov decision process, where is a phi tuple, right. There is a set S, which is a set of states, which is also called state space of the agent, the possible states, and there is set of actions, which is also called action space. There are typically the number of states and actions need not be the same, right. I mean, you can take them to be different, and there is transition kernel, which is the probability that an action AT being in ST at time t will lead to the state ST plus 1 at time t plus 1. So, take an action AT at state ST, what is the probability that you go to ST plus 1, right, at t, that is the transition kernel, okay. And there is a reward, this is a function from S cross A to R, okay. S is the state space, A is the action state. So, given that the agent is at state t and performs an action AT, what is the reward that the environment gives? So, note that reward can be negative, it is not R plus, unlike our loss function, right, reward can be negative as well.
But it's not, we are not trying to model it, it will anyway come from the environment.
Yeah, reward is given by the environment, okay. See, when you are asked to choose one of the two responses, right, they are modeling the reward. Every time you are giving they use that data to get the reward function, okay. And there is also this thing called discount factor, which it's simply a number between 0 and 1, and there is this distribution called initial state distribution, because the Markov chain has to start from the initial state, right, before it gets onto the transition. So, an MDP has this 5 tuple, right. S is the state space, action space, transition kernel, reward function, the discount factor, and the initial state distribution.
What is the second last?
Discount factor, it is a number between 0 and 1, I will tell you what that is, okay. Okay. And also there is a policy, okay. What is a policy? It is a distribution over actions given state. Now, note that you assumed, so what is the modeling problem here? Just like we modeled the underlying distribution, what is the modeling problem here? We assume that there is an underlying MDP that is governing this process. Example is playing an Atari game. There is an agent, environment, reward is being given. You have to, you want to design an agent that would play the Atari game, okay. There is an underlying MDP. What is that you want to estimate now? You want to estimate the policy, right. This also becomes a distribution estimation problem now, because policy is a conditional distribution. Now, given all this, I want to estimate the policy, the underlying policy that is governing it. So, how do you do that? Assume that it is a parameter. In fact, in RL, right, in deep RL, this policy is modeled using neural networks again. We know how to model distributions using neural network, right, use it for all applications. So, okay, so I will formulate that problem in a while. So, there is also this thing called trajectory, okay. What is data here? We need some data, right. What is you need trajectories of interaction. So, what is a trajectory? A trajectory is set of actions and states, okay, when you walk through this MDP. So, you start from S0, see what action the agent takes, and then go to the next state and see what action the agent takes, and so on. So, that becomes one trajectory. Collect multiple trajectories of this sort. So, what do you mean by that? You keep playing the game and then collect the states and actions, that is it.
But S1 and S2, they are sort of not in user control also, right, because they will change as per the reward.
No, see, when you are see, of course, start from initial reward, and but there is a reward. See, you are not, we are assuming that, see, for RL you need to have a fixed reward function. We assume that there is a reward function, we can't do anything about the environment. But given that we know what the reward function is, we can generate a trajectory by interacting with the environment, right? That's what a trajectory is. Data for RL is a trajectory, right? So when you are fine tuning an LLM, right, using RL, what could be the trajectory? Responses, prompt responses. That's what the trajectory is in the case of an LLM. What is the policy? The policy is the transformer. The model that you have trained itself is the policy. What is the reward? Reward is the choice that the human beings have made. Given two responses, if this is a better response, that is a better response, that's your reward. That is RLHF. So now you cast the entire problem of aligning a pre-trained LLM to human preferences as an RL policy estimation problem. That's what RLHF is all about. Okay. Okay. So let's formulate the problem. So since the trajectory, any question? Yeah.
So why not first estimate the reward function based on the reward
See, reward is something that the environment is giving you, right?
Yeah, but there is some.
You can only tweak the agent, not the environment.
But there is some underlying function which is.
Yeah, so we assume that the environment is giving us reward and we know what the reward function is. In fact, see, in the case of LLMs, one needs to estimate the reward function as well. Okay, there are these models called Bradley-Tukey model and so on, where given preferential data, like this is the response that I like, this is something that I don't like, there are ways to estimate the reward model as well. But we will assume, see, your RL methods are as good as the underlying reward function. Okay, that is something that's there. So we assume that the reward function is known. Okay, but there are methods to estimate the reward function as well. For at least for the formulation, let's assume that we know what the reward function is. Okay.
Can you see the supervised problem because we know what labels we want in terms of the reward and condition of the reward?
See, it's not supervised in the sense that the trajectory can be obtained. No, see in supervised, what happens is you don't continuously interact with the environment, so to speak. So you get the one sample from the distribution and you use that. But here you can keep going back and forth.
Here the conditional is different.
Yeah, but you keep going back and forth. That's it. So the environment interacts with you actively. That's the difference. Okay, so now we define what is called as a trajectory distribution under the policy. So what do you mean by that? What is a trajectory? Trajectory is a set that contains the states and actions, okay, when the agent is interacting with the environment. Now the trajectory depends upon policy. Do you see why? Because action depends on policy, exactly. So actually trajectory depends on two things. It depends on the state transition probabilities and also policy. It should depend on both, isn't it? Both the state transition probability, and because you what state it goes to given it is at a particular action depends upon the state transition probability, right? What action it takes depends on the policy. So it depends on both of them. Okay, that's why we can write a distribution over the trajectory. How do we write that? Use chain rule. Okay, what is it? Start from the state S0, that is governed by your initial state transition distribution. Okay, then from t equal to 0 to infinity, being at state St, perform an action At, which is governed by your policy. Multiply that with the probability of transitioning into state t plus 1, given that you are at St and At at time t. That's it. This is chain rule of probability, right? If you have a sequence of random variables, okay, that is governed by the underlying distribution, you just write the distribution over the entire sequence as the product of the conditional. That's it. This is the product rule. Okay. Now this is the distribution over trajectory. Now what is the goal of RL? Just like we formulated the goal in supervised learning, the goal in reinforcement learning is to learn a good policy. What is a good policy? You need reward to define what a good policy is. Just like we had the empirical risk, right, the loss function, similar idea here is that of the reward. Okay, define what is called as discounted return or discounted reward for a given trajectory. What is that? Collect the reward for at each state, each time step t, and multiply it with what is called as a discount factor. This is a number that we have chosen. This is a hyperparameter actually. So why do you have to multiply it with discount factor? the idea is the farther you go in the sequence, right, the less important the rewards are, because the system has transition for very long. So, you do not want the reward at each time to be equally weighted, that is it. So, this is a weighting factor, okay. That is what is called as discounted reward. I mean, it is simply scaled reward, okay.
So the most recent reward should be given over.
Correct, that is the idea, okay. Now, define the goal of RL as this. Take the expectation of the discounted return or the scaled reward. Expectation is over all possible trajectories. Let us say that you can interact with the environment infinite amount of times, you get a distribution over trajectories, okay. For every trajectory you have a discounted reward. Take an average of discounted reward over all trajectories and get a policy that minimizes that is it, optimizes the reward. You understand? Just like we had the expected loss function as the risk function, no, the same idea. Now, the expectation there was over the entire distribution of data, here the expectation is over all trajectories, all possible trajectories, because data now is a trajectory that you environment, I mean when you get while you interact with the environment. Make sense? So, the goal of all RL is to find a policy pi theta star that would maximize the expected reward. Is it okay? Now, you can solve this problem in 100 different ways. Okay, there is Q learning, you know, there are Bellman equations and so on. That is why I told you, right, RL is an entire course by itself, but I will only show you one way to do it, okay, which is called the policy gradient theorem, which is the method that is used for RLHF in LLMs. Okay. Policy gradient theorem is assume that, so you want to optimize this particular task, right. You want to find a policy that would maximize this expected reward. How do you do it? Just use gradient descent to do it. That is policy updating using gradient descent. Now, to do this, we need to find the gradient of the expected reward, isn't it? How do we get that is the question. And for that, we need this, you know, beautiful theorem called policy gradient theorem. Maybe skip the proof, it's very nice, okay. So, what happens is you can write the gradient of the expected reward, okay, in terms of this particular thing. Okay, what is this? Look at this. There is a gradient here of the policy, the log of the policy multiplied by the reward. The beauty of this entire theorem is that every term inside this is computable now. We know how to compute the reward, we know how to evaluate the policy. Why? Because policy is a neural network, right. This is the outcome of a neural network, right. It is a probability distribution that the neural network is imposing. So, we know what this distribution is. So, log of pi theta at given st can be found out, okay, and R tau is something that we know. Therefore, this entire gradient becomes computable. And this gradient, how do we get this gradient? Gradient of log pi theta at given st, how do we get this? Back propagation, no. If this is a neural network, I mean autograd is PyTorch way of doing it, but it is the normal error back propagation, that is it, because this is a neural network and we want, we can compute the log of the outcome of a neural network, and the gradient with respect to the parameters of neural network is something that we know how to do it using using gradient descent. Make sense? Yeah, this is the famous policy gradient theorem. In fact, it is taken to be one of the most elegant theorems that have come in recent times in ML, right, because this changed the way RL is being done. So, the classical RL does not did not look at policy gradient theorem, it looked at the other ways of Q learning or different ways of doing it, but yeah, so this is a very elegant way of doing it. So, now how is it done in the context of LLM is that you assume that your language model is a policy, and reward is what human beings tell you, whether they like this response or does not like this response, okay. Using that to use your RL to align the language models into the preferences that human beings have given. Okay, so there are other details, right, where you have this, yeah, so this is what I will show you. Yeah, before going there are some other details where you reduce the variance of this estimate, okay. what happens is this estimate that we have gotten for the gradient is shown to be noisy in the sense that it has very high variance. People came up with a lot of ways to reduce the variance of this estimate by using what is called as a baseline function, which would introduce to this concept of Q function, advantage function and so on. That is why you have these methods called GRPO and all that, right, which are the state of the art methods, which see all these methods that you might have heard about, right, PPO, policy preference optimization, DPO, direct preference optimization, GRPO, TRPO, all of these are variants of policy gradient theorem, okay, that uses different ways to reduce the variance of this particular estimator, that is it, okay. Yeah, so the last piece is how do you express an autoregressive language model as an RL policy. We already know that, right. To apply RL we need a trajectory. In the language model, initial input token, which is your prompt, is S0, the first state. The first output token A0, the first output token that you get by giving this prompt is taken to be the first action, okay. The second state is prompt plus first output token, that is your S1, and then it just goes on that way, right. So A2 is the output that you get for the appended prompt and so on. That is how you represent that as a policy. Sure. Then we have proximal policy optimization and so on, which is out of the scope of this particular course, okay. So yeah, this is about RL, right. So the striking difference is that instead of assuming that that you have data from an underlying distribution and you do not have any other way, any way to interact with the environment, you model the problem. See, this RL can only work in those cases where you can interact with the environment that you are trying to model, right. Suppose you have these kinds of problems where you have images and you want to solve a regression problem or some bounding box regression problem, there is no way that you can model that as an RL problem, because you are not interacting with the environment, there is nobody who is giving you a reward, right. Only if you can formulate the problem as an MDP, Markov decision process that I talked about, right, state, action, transitions and reward, then you can formulate the entire problem in the RL framework, and RL is known to do well if you can formulate an ML problem in that particular framework, okay. Okay, so that is it then, that is all I wanted to convey in this course. So a quick summary of what we looked at, right. I mean, started from probability theory, spent a lot of time on that. So saw how to cast the problem of machine learning as a distribution estimation problem. So all that we are doing is estimating the underlying distribution, okay, and we looked at multiple ways of doing it. Maximum likelihood estimation, basically the idea is to parameterize and then use a divergence metric and find the parameters by minimizing the divergence. And we looked at non-parametric ways of doing it as well, which are the Parson window and the k nearest neighbor estimation and so on. Then we looked at multiple ways of parameterizing this underlying distribution using different models, so to speak, right, in the empirical risk minimization framework, where we looked at linear models, the kernel machines and neural networks and different kinds of neural networks and so on. Then we also looked at some unsupervised learning techniques. Before that we looked at the other non-parametric techniques such as decision trees and the ensemble methods. Then we came to the unsupervised learning methods, where the idea is to model the marginal distribution rather than the conditional. There is no notion of a label here, and a special case of that was what was called as the self-supervised learning. We also looked at NCE and so on. The last part was the generative modeling, where you still model the marginal distribution, but the additional component there is that you also learn how to sample from the underlying distribution. And today we looked at RL, just an introduction to RL. So this is sort of broad taxonomy of what machine learning is. Write that block diagram, right, machine learning, deep learning and RL, self-supervised learning and so on. So all that can be seen under one broad umbrella of distribution estimation, right, given the samples. We also looked at ideas such as regularization, bias variance, decomposition and so on, okay. As I said, there is another course that is coming up, which will start from where we stopped here. So I assume that the audience know everything that we did in this course, and we look at the generative models in much more depth. We look at adversarial learning, the variational learning, flow based models, diffusion models, and score based models, energy based models, autoregressive models, and RL, and also some parts of state space models as well. So that's what the content of the next course would be. Okay, so hope to see some of you in that next course, and that's about it. And for the online audience, right, thanks for attending this NPTEL course on mathematical foundations of machine learning. So as I said, this is a course that would take a different approach for ML altogether, in the sense that instead of looking at algorithms themselves, if you have sat through the entire course, you would have now understood that ML is more about knowing what the foundations are, right, from the probabilistic standpoint, than understanding what the algorithm is. So algorithm is a byproduct, right? It's the core ML or probabilistic viewpoint that is what is of importance. So hope that you enjoyed the course. Thank you.